We have a great lineup of talks, starting with our first keynote session, an overview of the latest technical trends in radar, given by Dr. Joe Gersey, President and CEO of Information Systems Laboratories. Now I'd like to introduce our presenter. Dr. Joe Gersey has over 35 years of advanced technology development experience in industrial, academic, and government settings. The latter included a 7-year term with DARPA, where he led major new sensor and radar developments. He is an author of over 100 technical papers, publications, and book chapters, and a Life Fellow of the IEEE for contributions to advanced radar theory and its embodiment in real-world systems. He is currently President and CEO of Information Systems Laboratories. Now I'll turn the session over to Joe.
Hello, and thank you for joining us. So today we'll be taking an overview of some of the latest technical trends in radar, both from basic theory all the way through to those techniques and enablers that are creating new business opportunities. Of course, it's impossible to do justice to the entire field of radar in 20 minutes, but I did choose to pick a few items to dig down into that really look like they are going to be breakthroughs, especially in the next couple of years. I'd first like to start out by giving a shout out to a new journal dedicated to radar. And it may be surprising to some of you to know that there has not been a journal dedicated to radar in the IEEE. And thanks to the efforts of Professor Shannon Blunt and his AESS team, which is the Aerospace and Electronic Systems team at the IEEE, they worked tirelessly for several years and were able to launch a new journal dedicated to radar. This really speaks volumes to the vibrancy of the field, and is something that I hope all of you will take advantage of and contribute to. While we're talking about Professor Blunt and his efforts to get a new journal, we should also take this opportunity to highlight some of his research. He has a great team at his university that really have taken the shackles off of the types of waveforms that radar can use. In fact, I mean, he is taking it to a whole new level. You know, for many years, there were a lot of constraints on radar waveforms. First, because of the type of waveform you could transmit. You know, we love LFM, linear frequency modulated waveforms, because they make life much simpler on the transmit side, and they also make life much simpler on the receive side. However, they do have their limitations, and with the advent of new solid-state front ends, digital front ends, and of course, much more powerful embedded processing on the receiver, those constraints are now gone. And so the question is, with those constraints gone, what types of new waveforms could we use and to solve problems that previously we didn't think we could tackle? And so down below, you can see they've actually have a real radar system that they use to conduct experiments with these new waveforms. And you start seeing numbers with very different types of characteristics. I mean, time bandwidth products of 10 to the 6th is just an outrageously different type of waveform than what we're traditionally used to in radar. And yet you can see the results are really quite good. Now, of course, there's a price to pay. As I said, you do need flexibility on the transmit side, but you also have a lot more need to do offline processing to come up with the match filtering, as well as online embedded processing to do the match filtering in real time. And so when I said that Professor Blunt's team has come up with lots of waveforms, I'm not kidding. Lots and lots of waveforms. And here's just a partial list of some of those and the publication times and when they were demonstrated. What I find very interesting here is you'll notice that a number of them are quite amenable to both simultaneous radar and communications. This is a new burgeoning field. It's called integrated sensing and communications, or ISAC. So waveforms like this really are key enablers for that new technology, and that has a lot of applications in the commercial world, where you happen to have both a need to communicate as well as sense the environment, and that can be even indoors, for example, in healthcare settings. On the hardware side of things, of course, we've been seeing a lot of progress on multiple fronts over the past, especially 10 years, with RF systems on a chip, or RSOC, radar on a chip, the advances in terms of A to D converters. And so there's quite a bit going on that front. And in particular here, I'm just highlighting one of the really interesting developments is these very, very high performance transceivers, which, if you boil it down, is a high speed, high quality A to D converter with an embedded, typically FPGA processor, and then of course a D to A converter. So you could take in analog signals, process them in blinding speed, and spit back out a response. And this, of course, really addresses the test market for radar. And in particular, there's technologies like Artemis. You can see a link to it there. That's an acronym for Real-Time Electromagnetic Environmental Simulator, whereby now you can actually plug a multi-channel radar system into one of these transceivers and have it emulate the entire RF environment, which means, a pulse goes out, it interacts with the world, so there's clutter, targets, potentially EMI or electromagnetic interference, and all of that can be done in real time and sent back in a multi-channel format to the radar. So that basically means the radar can do virtual flight testing in a lab, but it's all real time and it's exercising all of the real-time software and all of the embedded processing. So while there's a number of enablers on the hardware side that continue to grow the radar, this is one I think that has not gotten as much attention as it should. And there's some links below there if you'd like to look into it further. Another enabler that might surprise folks, and this one I think has been a sleeper, is neuromorphic chips, which are distinct from, let's say, emulators like FPGAs doing things that emulate a neuromorphic computer. Neuromorphic meaning, neural networks, in particular spiking neural networks. So one company, BrainChip, for several years now has had a commercial chip on the market. And though it was originally designed to do basically image processing type AI algorithms, it has been shown that this technology can be adopted to do real-time embedded RF signal processing. And why is this important? Well, one, it implements AI, that's important, but really the huge payoff is in the size, weight, and power reductions that are possible. Typically, to do high performance embedded computing for radar in particular, you need either FPGAs or GPUs or ASICs or you name it. And that can quickly add up to kilograms and kilowatts. This spiking neural network, literally the size of a postage stamp or thereabout, it weighs grams and milliwatts. If you'd like to learn more about that, there's a link here to a YouTube video, or podcast, I should say, that talks more about this, and there's other ways to, in that podcast, to get further information on this. But This is not something that you typically think of as being associated with radar, but the impacts to reducing size, weight, and power are really a potentially game changer there, especially for UAV applications where size, weight, and power is at a premium. A perennial and ever-growing issue for all radar systems really in this today and into the future are confronted with an ever increasingly congested and in some cases contested and otherwise complex RF environments. The crowded spectrum problem is well known. That's why there's a desire to try to combine functions like combined sensing and communications. Contested, obviously, that gets you into the electronic warfare regime, which means that radars cannot just assume that they're not going to be contested when they go into certain environments. Complex terrain has its impacts, both natural terrain as well as urban situations where multipath and multi-bounce are the norm rather than the exception. And so these and many other factors continue to drive the need for what is called cognitive radar. And of course, let's not confuse the word cognitive with consciousness. Those are two completely different things. Cognitive is a well-defined engineering and scientific term associated with a system being able to sense and make sense of its environment and take intelligent actions as a result. Consciousness, of course, is something that science still hasn't really been able to nail down. So I just want to make, sometimes when we talk to different audiences with different backgrounds, there's an immediate visceral negative reaction because they think the word cognitive means consciousness, and I just want to clear that up. So what is cognitive radar and electronic warfare, which is also emerging recently? Well, again, everything from a theoretical point of view in radar, or EW for that matter, is all about the ability to understand the channel. And the channel is a theoretical construct which consists of everything that's in the path from the transmitter out through the environment and back through the receiver. Whether the transmitter and receivers are co-located or separated makes no difference. And as a consequence, that channel consists of all of the generally analog components in the transmit chain, including the antenna, and then out into the environment, which includes the atmosphere, the clutter, targets, EMI, whatever other effects, and then of course back through the antenna and the analog components before being digitized. So it's quite a lot, but any performance gains you hope to achieve, or any optimality, in fact, requires channel knowledge. And so I'm fond of saying, as goes channel knowledge, so goes performance. And so what helps you gain channel knowledge? Well, obviously you do whatever you can a priori before deploying your radar or jamming system. But you've got to do some on-the-fly adaptation, which means a sense, learn, and adapt cycle. And that learning phase can be quite elaborate and involve quite a lot of technologies, including things like knowledge-aided processing. For example, if you have knowledge of the terrain where you're flying, that can be used. That's an example of knowledge-aided processing, as well as AI techniques, learning techniques. So there's two books that sort of cover, one on the radar side and one on the jamming side, that I've highlighted here, in case you want to dig deeper into the theory and learn more about how the sense, learn, and adapt cycle can function. Here's an example of a radar implementing this cognitive capability. And it's in the form of a block diagram, and the reason for that is so that you can see a couple of things that sort of set it apart from traditional radars. And you'll see highlighted in yellow at the bottom is something called a real-time channel estimator. Now, that kind of thing was implicit in adaptive radars in the past. For example, maybe the adaptive beamformer was forming, from its perspective, some aspects of the channel. But in a cognitive radar, that channel estimation function is elevated to its own important level. You'll also see full adaptivity is a big feature, and you'll see also that adaptivity is key in the transmit side of the antenna, including MIMO techniques. Turns out MIMO techniques are very good for probing the channel and understanding what's going on, and then feeding back that information to create optimal and adaptive waveforms. As I warned early on, it's impossible to touch on all the great things that are happening in the field of radar, but chose to pick a few that I think really are going to have a very big impact in the future. And what I want to end on is one area that is glaringly needed to enable a lot of the concepts that you're seeing with unmanned aerial systems, or UAVs, UASs. So, for example, one of the vanguard programs for the United States Air Force is this collaborative combat aircraft concept, whereby let's say a manned system has a bunch of unmanned systems that are penetrating out in front, performing lots of advanced functions. And needless to say, many of those functions are radio frequency. So they could be a radar, they could be electronic warfare, they can be electronic intelligence, signal intelligence, radar warning receiver functions, emitter geolocation, all of these extremely advanced capabilities. And if anyone's familiar with these types of operations, you know that those functions span many different frequencies and thus have a lot of different antenna requirements. The question is, where are you going to put all those antennas, and how are you going to put them? Given the inherent size, weight, and power constraints that are on these types of missions, well, you pretty quickly find that you would really like your antennas to be conformal, but you'd also like them to be electronically steerable. And the little cartoon at the bottom sort of shows you that, well, traditional phased arrays are just too bulky. The way you get electronic steerable capability is with different phase centers, and that can quickly add up to a much higher size, weight, and power problem. There is a technology that's been implemented and proven now for several years. It's metamaterial antenna technologies, and as the cartoon shows, you can actually get electronically steerable capability with a single phase center. Somewhat ironically, you could almost have predicted metamaterial antennas before phased arrays. For example, pick up a textbook from the late 1800s and you know that the far field antenna pattern is the Fourier transform of the surface distribution function, as shown on the left. And if you can change the surface current distribution, you can change the far field antenna pattern. It says nothing about a phased array. And so researchers like David Smith at Duke University many years ago actually proved that it was possible to create metamaterial surfaces that could be electronically steerable from a single phase center. As I mentioned earlier, several companies now have successfully commercialized metamaterial antennas. Kymeta, for example, in the SAT communications world, and Echodyne in the radar world. These are commercially available. You can check out both the companies' websites and see the performance, and it's It's a proven technology. The key here is the underlying technology is such that it really lends itself to conformality as opposed to phased arrays. So this is definitely something that will no doubt play a key role in enabling some of these unmanned system concepts in the future. Again, my apologies for not being able to touch on all of the great things that are going on and new applications that are emerging, especially in health monitoring, things of that sort, automotive, which most people know about. But I did try to pick a couple that I think are going to have the biggest impact in the near term. So thank you for your time, and let's take advantage of the Q&A session.